So as you have seen on the Slack announcement, today we will discuss about hash tables. And you covered this part during the course. And I hope you have seen the two different ways of implementing a hash table. One way is to do probing, which involves a single array. And the other one is called chaining, which generally involves an array of lists. Now, each of the two versions have their own advantages and disadvantages. Now, what's the idea with a hash table? So why do we need a hash table? So arrays are the fastest data structure that we have. Okay, they have complexity 1 for accessing any element. Now, the biggest disadvantage is that they are very slow. Let's say they are poor on inserting and deleting. Okay, so they are not good at being dynamic. So for that, let's say we introduced a new data structure called a list. And those could be simple linked list or double linked lists. Now, a simple linked list biggest advantage is that it's very dynamic and it's very good at this, especially when you insert in front of it at the head. Now that will have complexity 1, or when you insert at the end, but you have an extra pointer to the end of the list, like we did last week. Okay, because otherwise its complexity for inserting at the end will be n. Each time you need to cover all the path from the beginning till the end. Okay, so arrays are fast for accessing elements, complexity 1, very slow or inefficient for dynamic resizing, adding or removing. Lists are very good at this, but they still are slow for accessing an element. Okay, because if you want to get to an element in the middle of the list, none of the two types, simple linked list or double list, will actually help you, because you need to start at one point, either at the beginning or at the tail. For double linked lists, we have the advantage of moving forward and backwards. Okay, so they have their own unique advantage, and their disadvantages like the other data structure advantage. So why not combine them? Because with a list, we will never be able to achieve the same speed as an array, but maybe we will be able to decrease that, okay, to a point where we can say we are in the middle, we are using advantages from both arrays and both lists. So we have a new data structure, which is like a hybrid that combines the two data structures or the concepts from the two data structures in order to give us something which is not the best at both criteria, but good enough. Okay, so it's neither the best or neither the slowest, depending on which criteria do you see. And this is a hash table. It's a hybrid data structure which has an optimum point for either inserting, removing, and also for accessing elements. Okay, so that's why we use hash tables. Now, it has something that the others don't. And here we introduce a new concept called key. So each element will be identified by a key. And we will use this concept for the rest of the semester when we will cover the best data structures for searching, which are trees, binary trees, n order trees, B trees, balanced binary trees, and so on. So we will have several weeks just on trees. Okay, so we introduced this new concept, which means that each element, each value has a key that we will use in order to identify it in the data structure, in the hash table. And every time you have a data structure which is using this concept, a key which is associated with a value, this is called a dictionary type data structure. So the entire family of dictionaries are generally based on this concept. A key which is associated with a value. And when we say key, you know this from databases, the key should be unique. Okay, so every time you hear key, you need to think instantly to this property. The value is unique inside the collection of keys. Okay, now you encounter hash tables at object-oriented course and also at the Java course, where you used map types, and this is from C++, the hash map type. And in Java, I think you used at some point hash tables. Okay, so this is actually the name of this data structure. Okay, we don't have time to cover both structures. I will just give you a glimpse of how they look, just a reminder of what you have discussed during the course. And after that, we choose which one do we implement today together. So we don't have time to cover both data structure, both implementations. So we need to choose. But in order to choose and knowing what we will choose, let's do a summary. So at this point, you know why we need hash tables, because they provide optimum values for accessing elements, and also, so they are faster than a simple linked list if you go by that solution, but they are slower than an array, and they have an optimum point for inserting and deleting. So they will be faster than an array at this, but they will not be, let's say, as faster as inserting in a single simple linked list at the beginning. So like I said, they are in between. Okay, so now what's the difference between probing and chaining? Generally, probing is based entirely on an array. Okay, I shared the paint. So this is the probing approach, at least the schema of it. So just think as an array. Okay, so we have a big empty array with different values, with empty values here, and we can store our data here. Okay, so let's say this is the first, the second, the third, and so on. And now, in order to add something here, based on a key, and we will see how to determine that key, and the way you do that is consistent over both implementations. So the algorithm that it's using the key in order to determine the location of the element based on its unique value here is the same. Okay, it's generally the same. You process that value and you get an index. So when we want to insert something here based on a key, let's say we want to add a product, and let's say based on that key, on this key, the algorithm will determine that this is the location here. So the product with that key will go here. Now, another product with a different key, let's say this is K2, we will process this value, and that value will go here. So you see this array, which was initially empty, is starting to filling up. Okay, we don't have so many available free spaces. And at some point, because this is a limited space, and the function that is processing the key will always generate a value here. Let's say this is index 0, and we have initially n values, but we will always, by processing the key, we will get a value here. So at some point, we will have a different key, and just imagine you have an infinite, almost infinite space of keys. Just think for values from 0 to integer max, and here we have a finite space from 0 to, I don't know, 1000. It's obvious that at some point you can't store 2 millions and something, 2 billions and something unique keys in the same array of 1000 locations. So which means that at some point we will have a new key K3, and for this key we will have a collision. And the collision means that processing this key with the same function that we use for K and K2, we will have the same location. So normally here, you see the keys are different. This space is already occupied because another key, which was processed by our function, generated this index. So we place that value here. But now we have a different key, it's not the same one, and now we got the same index. And like I said, it's normal. Here you have a finite space, a limited space, and here you may have an infinite or a huge space of different unique keys. So what do we do here? And probing, actually probing, you know the word, which actually means to investigate. Probing means if you find a collision, if this location is already occupied, probe the next location to the left. So here, if this is occupied, we need to place this value with this key here somewhere around here, because when we will search for it, we will use the same algorithm. So this is occupied, and I will look to the next one, and this is free. So we are lucky, we will place the value here. And now let's say we have another value, another k, k4, which is different from 1, 2, 3. So at this point, we compute the value. The function is called the hash function. That's why you have the name of the data structure, hash table, because the function that processes this key and generates this index here is called the hash function. Okay, and now let's suppose we have the same collision on the same location. Now, space is already occupied. We probe the next location, is already occupied. So we continue probing. And we generally we stop when we find the first free location, okay? Now, let's suppose that these locations are all occupied. So we probe, 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 we reach the end. What do? Start from the beginning, okay? So each time you reach this point and you need to probe, you go from this location. Now, what will happen if the hash table is already full? We need to resize it, okay? And generally, because we need an optimum point, we will actually resize the hash table, not when it's full, because, you know, when you do that, insertion will take a lot. You need to probe all the other locations. So it's like inserting at the end in a simple linked list, you gain nothing. It has the same complexity. So we need to be smarter than that. And generally you have let's say, occupancy degree, or what's the percent of available spots in this hash table. And generally, when you are about 60, 70%, you will resize it. And the easiest algorithm to resize is to double the size of the array. So each time you fill up this initial array up to 70% of all available locations, you resize it. And in this way, you gain new locations. Obviously, you update the hash function, because if you resize it, you need the function to be updated, so it will give you values here. And you will use the other locations. Okay, so this is probing. Now, the opposite, okay, it's still based on, no, cancel, I don't want to save it, new. It's still using an array, but the array has a different purpose. And this is chaining. So in chaining, you use the same approach. You have a key for which you compute the hash value. And let's suppose you get locations here. So at this point, the array looks the same. Okay, so based on K1, let's say you get this value here. Now, when a collision will happen, probing means search the other available locations to the right. If you reach the end, go back and search from the beginning. Now here, we need to change that. So here you see chaining is let's say the perfect example, or the proof that a hash table is actually a hybrid data structure. So instead of probing here stuff, we will actually store at each location here a simple linked list. Okay, so you see this is actually a hybrid. So each point here is actually managing the head of a simple linked list. Okay, so based on the key here, you compute the index, you will find this, so the value will go here, let's say K1. Now you get a new value, K2, you compute once again the hash value. Let's suppose we have a collision, so they will be on the same location, which means in the same list. So now K2 will go here. Now we need to be smarter than inserting here at the end, because we want to always be as close as possible to the optimum. Now, this array will speed up things, and it will take, it will be significant, because if this array is big initially, can easily determine its locations here, okay, each list, because we know the complexity of accessing a value inside an array is 1. And in order also to speed up things here, not to lose time by inserting at the end, here we will always do insert at the beginning. So this is like K2 will be now the first one, and K1 will be now the second one. So here we will always insert at the end, and we will use this array to manage all these simple linked lists. Okay, so this is chaining. Now, how do you search stuff here? You want to get the details of a product with this key. Once again, you use the hash function. The value given by that function will say, hey, look in this list. And now you do a recursive search here based on the K2 value. Okay, and you will find the element. So this is an optimum point, and probing the same between using only arrays and also using only simple linked lists. So hash table is not the fastest for accessing or for inserting, is the one that will give you an optimum point between the two data structures, okay? Which is for large data sets, it will be more efficient rather than using lists or arrays, okay? Because you have a large volume of data, in the end, you will see the efficiency. Okay, so this is the short description of the two approaches, a vector of lists or just a vector. So in order to decide, okay, I will wait 10 seconds more in order to choose, but I can already start defining our malloc. Let's say string. Okay. Okay, so okay, we have the final result. So chaining 16 votes, probing only 6. Okay, I close the, so I will share the results. Okay, now you should see the results. Okay, so we will go for chaining. Okay, I will close the, okay, the poll. Okay, so malloc string, standard input output, and I think that will be enough. So let's start with the data structures. Now, what we want to store, let's store a product. So generally, I will want to be able to check available stock for a product. So I will go for a char description. No dynamic fields. Okay, price, and we need the key. So for the key, I will go for a char, let's say to the barcode, and the barcode can contain digits and letters. It's mostly digits, but let's keep things open. So let's say there are different standards. So I will go for a barcode of 50 chars. So the key here, it's an array of strings. I want to go for an array of string because I want to show you that the key could be anything, not just a number, okay? Numbers are just particular keys, but it could be anything. So we will see how to process this barcode. Okay, so description, price, available stock. Okay, so we have a large database and we want to store, to manage our products, and we want to be efficient when someone will try to make an order. Maybe they will want to see the available stock and the price. So they want to see the details of that product. You see the guys in the hypermarkets or stores, they have their smartphones and they are checking available stocks in order to update their store. stock and so on. So this could be an application for that. Okay, so this is our data that we will manage, is the product. Now let's define the data structure for the hash table. So it's an array of lists, simple linked lists. So let's start with the list node and node. Let's define it with node. And here we have a product as data product. Okay, and being a simple linked list, we need the next reference. So this is the node inside that simple linked list. And the hash table, as I said, it's an array of heads or pointers to lists. So in order to manage a list, we know that we need a pointer to the first node. So our hash table data structure looks like this: struct hash table. Okay, and we have this, an array of pointers to nodes. Now, because at some point we need to resize it, even the chaining approach, it has this problem. If you have a lot of collisions on the same locations, those simple linked lists will grow to large, let's say, number of elements. So each time we will query the hash table, we need to go and traverse all those long simple linked lists. So in order to avoid that, as for probing, at some point we can decide that, let's say, the maximum values that we can have in a simple linked list, it should be, I don't know, the double of the array size, initial array size. So when we reach that point, when we have a lot of big simple linked lists, we will resize the array. So in order to be able to resize it, we can't go for a static approach, okay? We need to be able to resize it. So in this case, this is a dynamic array of pointers to nodes, okay? It's a dynamic array, I know that, because I want to resize it whenever I need to do that. And this is the array itself, array of lists. Okay, and let's initialize this as the other ones, just to be sure, equals 9. Okay, just to not forget later. Now, when we have an array, we know, and that's another disadvantage when you compare them to lists, you need the size of it. Okay, so we need to store or to manage the number of elements, okay, or number of lists, but let's say number of elements. Okay, and I think this is everything. So this is the hash table. It's just an array of pointers to simple linked lists. Okay, and in order to hide this, because maybe I don't want to see the hash table itself, I will define another structure called products catalog, or dictionary, but let's go for catalog. Okay, and it will manage for us the hash table, and we will also give that a name. So description, this is the store name. Let's go for store name 50 chars. Okay, and we need to handle this this part here, the hash table, and I will have a hash table, let's say the catalog or dictionary. Okay, so these are the data structures that we will use. The product data structure, the node, which we already used before, so we know this, why we need this. Now a hash table, maybe at this point this is different because we have a dynamic array of pointers to node, which we know that they are actually simple linked lists, the number of elements here in the array of lists, and the products catalog. Now let's start with creating our own functions just to manage all this stuff, the creation of that stuff. So I will go for a product, create product. Okay, just to have it. Okay, so we need the description, price, stock, and barcode. So const char description, float price. I think the stock, because it's yeah, the stock, it's an integer value. Okay, it's the number of items. Okay, we can't, I don't think we can have half of a product and sell it. Okay, so stock, available stock, and const char, what was that? Key, the barcode. Okay, which should be unique. Okay, now let's initialize them. Now, if they were dynamic, we need to allocate space. That is not the case. So string copy, we need to create a new product here. Product. Let's copy product. Yeah. Expected, yes. That's right. Okay, so string copy product description, product price equals price, product stock equals stock. Okay, and the last one, string copy product barcode equals barcode. Okay, so we have our yeah, it's not equals here, it's a comma. Now we know how to initialize a product, so let's return it. Product. Okay, so this part is already covered. We don't need to worry about this sequence of 5 lines of code. Each time we need a product, we know how to create it. Let's move to the other creation of a node. Okay, create node. So here we need a product. You already know that, that's why I'm not asking, because we covered this part many times. Okay, and here we will create a node. So node, new node equals node alloc of size of node. Okay, and because you have we don't have dynamic fields, because we don't have pointers in product, I can copy them like this. Now, if you have dynamic fields in product, what I recommend you is to do something which is like overloading equals, if you remember that from object-oriented, which means I will just give you the header. Okay, so let's say if you have pointers in your structure, use this function to copy them instead of equals. Okay, we know that equals will do shallow copy. It will do copy paste, so you will have 2 data structures sharing the same space, which is not okay. So here you should do what? Product, copy product of another product. This is like the copy constructor, if you like, product B. Okay, and you should actually copy, and when you encounter the dynamic field, you create new space, string copy if it's a string, or if it's an array of values. Okay, so whenever you have dynamic fields, create this function and use it, because here you see, because I don't have dynamic fields, I can write product equals product. But if we were to have, maybe next week I will remember and take a dynamic field, but in that case, here instead of writing this equals, I will use copy product. It will be like new node product equals copy product. Okay, and I will copy it. It will create a new array in heap, a new space in heap, and in that way I will be sure that I'm in control of that space in heap. And the last one, even if we initialize it there, I will always write this, because maybe at some point you will use either of these two initialization and you'll be okay. So that's why I'm being redundant here, because this is very important. Okay, so we know how to create a node. Let's create the hash table. So in order to be efficient, and remember, adding or resizing an array, it's an inefficient operation. It costs a lot in terms of performance. We want to create an initial hash table, and this also is available or valid for probing. You need to start with an existing array with a given size, and at some point you will resize it, but you need to start with a given array. Yeah, with a
we
size.
should return the new node.
Yeah,
on the function.
Yeah, thank you. New node. Okay, yeah, that's why we need to compile things, because otherwise we can do mistakes. So we will start with an initial array. So for that, I want to create a function called init hash table, because we will init it only once. What's this? Okay, so, and after that we will resize it. So we will have a function to resize it. So hash table, init hash table. Okay, now what we want here is the initial size. So we will get that int initial size. Okay, so let's define an empty one, hash table. Okay, and in order to initialize it, we will do this: hash table number of elements equal initial size. Okay, and now hash table array of lists equals with malloc initial size multiply with size of each node. And each element in the array list, if you forgot, we need to go back to the definition. This is the type of each element here in this array. It's a pointer to a node. It's not a node. It's a pointer to a node. It's actually the head of that simple linked list. So size of node asterisk. So it's actually an array of pointers to lists. And here, this malloc will return a node, a pointer to an array of pointers to node. Okay, or if you want to write it like this, but generally I think this is more clear why we have two asterisks. It's a dynamic, it's a pointer to a variable that will store pointers to node. Okay, and return it. Now, why it's important to, for simple linked lists, why it's important to initialize next to null? Why do we need to do that? Why do we initialize always next to null for a new node?
So we could know when the list is ended.
Exactly. So without that information, we will get easily into trouble because we will not know when the list terminates. So null is very important to that pointer. Now, what do you think for this hash table right now? We have an array of pointers to lists. What's their value now?
0xCC.
Exactly. I don't know, maybe they change that. Depending on Visual Studio, you can get 0xCC, or we are lucky we get null, but we will always want to be sure. Maybe we change the compiler, and the new compiler is setting neither 0xCC, but also neither null. So null here is very important because in this way, we know if that location is used or not. Because we have an array of pointers to lists, how do we know we have a list there? Because initially the array has 0 lists. It can manage a lot of lists, but we don't have them yet. We need to start getting products. And in that way, we get our lists. So don't forget when you create a hash table to initialize all those pointers. Okay, so in order to do that, I will go through all the pointers. Int I at 0, I less than hash table dot number of elements, I++, and let's initialize them. Hash table arrays of list at index I equals null. And now we have the possibility to check when we insert something or we search for something, if that list exists. For probing, the array it's storing actually products. So when you go for the probing approach, you start with an initial array of products with a given size. What do you think? How do you determine if the location is empty or not? Because you will have an array of products. What will be the solution there?
We can put, for example, the price equal to -1.
Exactly. You use a flag or something, an attribute of that product, which you know that it will never be -1, and generally you will use that value. Normally, you should use a default value for the key, because remember, the key will be the one that will actually decide where the product goes. So here for barcode, you can actually set the first char to \0, which actually means empty char. So in that way, you know that the location is empty because you don't have a barcode. Now, if the ID was a numeric value, what your colleague said, using a negative or a -1 will be perfect, because let's say we don't have negative indexes. Okay, so in this case, we set all the pointers to null. For probing, you need to choose the ID, a default value that you will reuse later in order to determine if the location is used or not. Okay, so we know how to init the hash table. Now let's create the catalog, products catalog. So init catalog. We need the name, const char store name. Okay, let's create the products catalog. Okay, catalog. And I think, let's call it dictionary, or yeah, dictionary, because we have a catalog dictionary inside the structure. So string copy into dictionary without an S, dictionary store name. Okay, and now we want to init the hash table. So it'll be like this: dictionary catalog equals init hash table. And generally, the most used algorithm for resizing is this one: multiply the size by 2 and add 1. Okay, so our hash function will be generally, and most hash functions will be based on modulo. So I will choose here, and you will understand in the next minutes why I'm using this value. And this is actually what Java is using, or it was using for its hash tables. And I will give you the reason for that in the next minutes. 101. Now, 101 is not just a value, it's a primary number, and this will matter. Okay, and it's also looking very good. It's 101. Okay, but it's a primary number. This is why I choose this number, and it's not just a primary number. You will see that in relation with the hash function that we will use, this is one of the best primary numbers that we can use. Okay, so we know now how to create the products catalog. Let's test this. Maybe we have other things we are missing. So let's test this. So you see, using all this cascade of simple functions, now
You have to return the catalog.
Yeah. This is, I think this is something that describes me. I forget to return. Okay, so dictionary, or anyway, thank you for the help. So in order to initialize the products catalog, I will just say products store catalog equals init catalog. Okay, let's say my store. Okay, So we have this hash table. Now we have it. It's an empty hash table. It has an initial size of 101 lists or elements, but we have 0 products there. Okay, so in order to test this, let's once again go for a function that will print a product. This will be our way to test the hash table. We will search for keys and we will print the products at that location, or the details of the product with that key. So once again, we need the void print product. Okay, and printf \n. I will start with the description, or let's say product. Okay, like this, %s. I will put the price, %float. After that, the stock, %d, and the barcode, %s again. And here I will have product description, product price, product stock, and barcode. Barcode. Okay, so this will be our function that prints the details. Okay, now generally it makes no sense to print the hash table, and that's why, if you remember from object-oriented course in C++, when we covered the standard template library and maps, you can't iterate through the map. You can get a collection of keys, but you can't iterate through the map, okay? Because it doesn't make any sense. You don't know what's their order, and this is not the scope of a hash table. Its scope is to behave like a dictionary. If you want to search for something, ask for that key. If anything there, you will get the details. Otherwise, you will get nothing, okay? So we don't want to implement a print method for hash table. Okay, so what else do we need? We need a hash function, and we can't have a hash table without the hash function. Let's say the hash function. So what's the scope of a hash function?
Determine the position.
Exactly. So it will take the product barcode. Okay. So this is the, let's say this is the input. It will take the product barcode, and the output will be
A product?
no. The hash function will help us to just determine which is the list that
The table size.
The
no,
index of
exactly the index of the list that may have or not. We need to do a sequential search there. It may have or not our product. So if I go back to this drawing, is the last one, so I still have it here. You see, the hash function will take the key and it will say to you, hey, the product may be here or not. But from my perspective, this is the location that I determine based on the key, which is the index of this particular list, or this one. So at this point, we need to do a sequential search here in order to see if we have the product there with that given barcode or not. And this is the only utility of a hash function. It's a hidden function that will always help you navigate in this array. And that's why we have this optimum point. Remember, you have a function that will process something and it will say to you, I think the product is here. So what's the advantage? By knowing this location, the index, we use the advantage of an array. We place ourselves here in an instant, right away. Remember, they have access complexity of 1, which means instant. So the hash function will help us navigate in this array and avoid doing a sequential search in this array by checking each list at a time. No, the hash function is saying, don't look in the other lists. This is the one that you need to search for that barcode, okay? And this also goes for probing. Okay, so the output is the index of the list that may have, you don't know for sure. Remember, it's like searching something in a dictionary. Maybe you are searching for a wrong name. You don't find it there. So that may have or not. So output the index of the list that may have or not the search product.
We don't need to input the product barcode and the table size.
The hash function must return a value, which is the index, and that's it.
Okay.
Now, how do we compute that index is what you said. Okay? But we need to return a value. So the index of the list that may have or not the search product, and not just the search product, the search product or the product that we want to insert. Okay? Or we need, yeah, let's say we need to insert, because sometimes we insert something, sometimes we search for that, or sometimes we delete that. So the hash function is returning a number. If we want to navigate in an array, we need an index, and the index is always a integer value. Exactly. So hash function. Okay. So what do we need in order to compute the index based on the product barcode?
The key.
Which is the barcode in our case.
Yeah.
Okay. And do we need something else?
The table.
The table or something from the table?
The length of the table.
Exactly. So I will write here another interesting property. The return index is between, because otherwise you will have a runtime exception. You will be out of index, out of the array, between 0 and array length. Okay, and in order to be sure that we are here, we need here an int table size. Okay, now we have an almost infinite range of possible values. So let's see here. We have barcodes on 50 chars. If you try to compute what's the number of total combinations of all possible barcodes that are using digits and symbols, alphabetic symbols. So you have an alphanumeric barcode, you will find out that there are millions or even billions of possible combinations. And in the end, we start with a hash table with initially 101 values. So obviously we need a function that will take this huge amount of ranges, possible ranges for the key, and in order to return a value between 0 and 101, which means 100, because we know that the index in C, yeah, let's put here, -1, is between 0 and n-1. Okay, so the perfect function that will always give you an output in a well-defined limits is modulo, the algebraic modulo, and for that we have the modulo. Okay, here, this is the operator. So if I'm giving you any value, any value, just imagine any integer, positive integer, and if you do this function, x modulo 101, you will always be sure that the output is between 0 and 100, because this is actually the reminder. It's like dividing the x value to 101, and you will always get the divider, okay? And the divider is always 0, the remaining part, okay, to 0 to 100. Okay, so this will be our function here. Now, the only problem that we have is how can we take a barcode and generate a value? So we know that a barcode is an array of charts. And we know
ASCII code.
exactly. And we know that charts are actually numbers. So why not adding them? Let's add them. So let's say this is the int barcode ASCII sum equals 0. So for integer I at 0, I less than, let's say 50, because this will be the maximum number of charts that we may have in a barcode. Now, instead of writing 50, maybe that will change in time. So I will put here a comment. We know the barcode is a fixed size array, chart array. And this will help us because maybe in time we want to update, extend that. So
Can't
here I
we
will
just use strlen? Yeah,
or we can just use strlen. What I wanted to say here, size of, okay, let's go for strlen. If you want to continue my idea, here will be size of the this one here, the product barcode. But I think it's better to use the strlen. Okay, so I think it's more obvious. So I less than string length of barcode. And in this way, we avoid also backslash 0. Okay. I plus plus barcode ASCII sum plus equals barcode at index I. Okay, so this is one way of transforming a string or an array of charts to a number. You just add the ASCII numbers. This is what Java is doing for string type keys. It's doing a sum. You can look for that over internet, but it's generally using the ASCII codes and it's doing a sum. Now, so let's hope that will give us a unique value. It will not happen, but we expect that. Hash tables are based on collision, so that will be not an issue. So here I will say return barcode ASCII sum modulo table size. Okay. So in this way, for any given barcode, we will determine the index. Yeah, let's write this index in order to help you remember what's this. So return index. I will just name the value. And a semicolon here. Okay, so this is the hash function. Okay, now we need another function before moving for insert. And the other function is called resize. So at some point we need to resize the hash table. So void resize hash table. Now, when we want to resize a hash table, what do we need?
Its size.
Sorry? Its
the
size?
hash table.
The hash table, because we want actually to rebuild the array inside the hash table. So we need the hash table. Now, is this hash table going to change inside the function? Do we need to change anything? Yes. So let's pass it by a pointer. Okay, so this will resize the hash table, and generally we will create a new array with a different size, but we want to preserve the existing values. Okay, so in order to do that, we need to define the new size. Int new size. And like I said, the most used algorithm for resizing hash tables, and it's what's everybody talking right now about exponential growth. And in order to have an exponential growth, which means for hash tables that need to grow fast, we will, by doubling its size, we have an exponential growth in terms of size. So it's like we need in the future to do less and less resizes, because by doubling the size, the capacity is increasing faster than the new values will go into the hash table. Okay, so in this way, by using an exponential growth, we don't need to do as many resizes in the future. Even if you reach 1 million products, maybe you will do, I don't know, 3 or 4, 5 resizes in order to store that 1 million products. And doing only 5 resizes, that's very, let's say, cheap. So that's why we need a function that will increase the size in exponential growth, and doubling that, it's perfect. It's a power of 2. So the new size is hash table dot number of elements multiply with 2. And if we stop here, because modulo here, we are using modulo here in order to determine the index. And we remember we started with a prime number, because a prime number, it's less frequent to be a divisor of other values. You will find the most common divisor is 2 or 3 or 5. But for prime numbers, there are less and less values which have this, which are multiple of that prime number. So in this way, by using a modulo and a prime number, we can actually distribute. We will have as close as possible to a normal distribution, which means the values will not stuck in some particular lists. It's like they will go all over the space, because you have less and less values which are a multiple of a prime number. Okay, so that's why they choose prime numbers here, in order to make, let's say, a normal distribution over the entire space of possible indexes inside that array. So why do they choose 101? Because, like I said, it's a prime number, but it's, let's say, more special than other prime numbers, because this is the prime number that will give you the largest sequence of other prime numbers generated based on this formula. So 101 multiplied with 2, it's 202, plus 1 is 203, another prime number. 203 multiplied by 2, it's 406, plus 1, it's 407, another prime number. Now, multiply that by 2, you have 414, plus 1, 415. Now, this is not the prime number. But if you multiply it again, you will have 830 plus 1, 831, which is another prime number. Okay? And the story will go on. So that's why they choose 101, because it's the prime number that will give you the largest sequence of prime numbers, but also other numbers generated by this. Okay, so this will be the resize hash table. So Java is using this approach. Okay, what do we need to do is to create a new array. Okay, new array equals node, we already know why, malloc with new size multiply with size of node pointer. Okay, don't forget to copy the previous values, don't forget them. For int I starting at 0, I less than hash table number of elements, I plus plus, new array at index I equals with the hash table, it's a pointer array of lists at index I. So now we copy all the other values. Don't forget here that here we are creating an array with either 0xCCC or other values. Maybe we are lucky and we will get null, but I don't know for sure, so let's be sure. So for int I at 0, not at 0, actually starting with number of elements, I less than new size, I plus plus. So we need the other pointers, we initialize them with null, because otherwise I'm not sure if there will be none. Okay, so the rest of them. And now what do we need to do? We need to delete the previous array remember what you is not delete, sorry, it's free. So here does matter the brackets. So free hash table array of lists. Now the list will not be deleted. We delete only the array of pointers to those lists. Okay, no one deletes the list itself. And now don't forget to get the new array. Sorry, it's hash table. Array of lists equals new array. Okay, and that's it. So this is the.
Actually, you didn't modify the size of the hash table.
Okay, and also that. Yeah, thank you for that. We will have some troubles later. So hash table number of elements equals new size. Yeah, thank you for that. Okay, now we are done. Okay, so we generated a new size, we created a new array list, we copied everything from the previous array, and now we initialize the other pointers with null, and we remove the array, just the array, not the lists. Okay, we save their pointers here, so we have them, and now we change our hash table. Okay, so we have to implement two functions in order to have a hash table that we can use. So one operation is to insert a product, and the other operation is to search for a product. Okay. Now, in order to manage the insert in hash table and reduce the complexity, when we describe the hash table, the chaining approach, I said to you that when you choose to insert in each list, each managed list, go for insert at the head because it's the fastest insert. So once again, we want to be performant, okay? We want to be fast. So let's handle this part. We actually have a list of nodes. So I will create a function that we will use in order to insert at the beginning of a simple linked list. So I will use this function in the insert into hash table function. So every time we insert in a simple linked list, we have a new node, right? Because by inserting at the beginning, you have a new node. So node insert at beginning, so at head, let's say, and we need the existing list, head, okay, and we need a product. Product. Okay, now every time we insert something, we will have a new node. So we have a function for that, create node product, and inserting at the beginning, product with the small p. It means, and it's a very simple insertion, means the new node next is actually the existing head. And in this way, we also cover the case where we have an empty list. Just imagine that this pointer is null. New node next equals null. Okay, we already were there, but you see, we don't need extra special care for this case where the existing list is null. It's empty, because actually nothing will happen here. But for all the other cases, this will also work. So once again, it's a very simple way of inserting in a list, which is actually covering all special cases. So new node next equals head, and return new node. So here we choose to return each time after inserted head the new node. If you remember, in previous examples, we were actually changing the head here, or the structure that was managing the simple linked list. Now let's go for a different approach. So we return the new node, okay, which will be the new head. Okay, so this is inserted head. Okay, maybe if we are here, let's also do the sequential search function for a simple linked list. So this will return a product, search for product. So we need what? The head of the list, the simple linked list head. And also we need a product. The barcode. Barcode for that particular product. Now, this is a contract that we need to comply to. We need always to return a product. So let's just prepare for the cases where we don't find a product with this barcode, or maybe the head is empty, which is non-pointer, which means we don't have any list there. So product, let's say result, we just created one. So in this case, in order to say that we don't have a product here, let's go for this approach. String copy, or string copy, result dot description.
Why don't we use the create product function?
Very good suggestion. So equals create product. So description will be none, and we know that we have a product with none. Price will be -1, stock -1, and barcode, empty barcode. Okay, so in this way, this will be our way of telling there is nothing there. Okay, we didn't find anything. Okay, so how do we search in a simple linked list? Now let's cover the special case. If head is null, return result. Why waste time? Now, if we pass this check, it means we have a list that has at least one node. So for node P starting from the head until P is different than null, which means we exit the list. P will be P next. And in this way, we go through the list. Let's see if those products have the search barcode. So if P product, if string compare of P product dot barcode and barcode. Okay, we know that string compare returns 0 if string compare without these brackets here. So string compare returns 0 if they are equal, and this is what I'm searching for. It means that's it, we found it. Why staying here? So return P product. That's it. We exit the for loop. We exit everything. Now, if we reach this point, result, return result. Okay, so this will finish everything here. We exit the for loop. We exit everything. We don't care. We found what we were looking for. If we reach this spot, it means we have no product there with a given barcode. So we return it. So now we also have the search for product. So we can query the hash table. Okay. And the last function will be insert into the catalog. Okay. Which means insert into the hash table itself. So void insert product into catalog. What do we need? We need the products catalog, which is actually the hash table or dictionary. And we also need a product. Product. Okay. We can check just to be sure that the dictionary is created. Maybe we forget to do that. So if dictionary catalog, and this is the hash table, array of lists equals null, return. okay? Maybe here we have this int, and in this way we can check if this has succeeded, okay? So here we do a return 0, which means we can't insert that. Okay, now if we are here, it's obviously that we have an array of lists. So let's use the hash function in order to determine the index of the list that will contain this product. So int list index equals with hash function of product dot barcode. Now we have it. Will be a value. Sorry, we need another argument. Table size. And in order to take the table size is dictionary, catalog, number of elements. Okay, so now we have the index. It's obviously between 0 and number elements minus 1. Okay.
I have a question.
Yeah.
If we modify the number of elements in the hash table after the resize, the hash code for every element isn't changing?
So let's suppose here we have different barcodes, right? That will give you, let's say, barcode equals, I don't know, A, B, C, D, 23, right? And for this barcode, we get the index, we get the sum 200. Now, when you do 200 modulo 101, okay, you get what? 99. Okay, it's 99. Okay, now, yeah, it's a good question because I'm seeing the same thing what you was asking. So the ASCII sum is now the same, and now we have increased the table size to 203. So in that case, 200 modulo 203 will be 200. So the same ASCII sum will give us a new location. So we will search for existing items at this barcode. And initially they were in the list with the barcode ASCII sum 200, which means in the list 99. And now after resizing, when we will search for this code, we will actually search it here. And obviously he's in the list at index 99, right? This is what you were asking. So your colleague was saying this. If initially we are using this hash function, okay, and we have a table size of 101, we will insert a product with this barcode, and based on the function, and we assume that this ASCII code sum will give us this value, okay. At that moment, the index given by this formula will be 99. So in that array of initially 101 lists, this product will go into the 99 one of them, okay, to the one at index 99 or position 99. Okay, after we resize the table and the new size will be 203, using the same formula, the ASCII sum will be the same, okay, 200, but now modulo 203 is 200. So we have already the product and we want to search for it. In the meanwhile, the hash table has been resized. So at that point, using the same give me the index of that product, we will search him for it into this list at position 200. And it's obviously that it was inserted at position 99, and now we are searching it in a wrong list. So in order to do that, we need to reallocate the lists. Now, let's finish insert product into catalog, because we will actually need this function later in order to insert into that, or no. No, because I will delete this example. Okay, thank you for the last argument. So I think the way that we will do this and be sure that everything will work, maybe we'll find another way of doing this more efficiently, we can search for other solutions. So this idea with relocating is wrong. We can't relocate. You just give us the argument. What colleague was saying, if it's not clear, initially when the size was 101, we can have two different products that will give us, let's say, the same index based on modulo 101. So let's say it's index 0. And later, when we increase the size to 203, the same two products, modulo 203, will give us different locations. So it's not sufficient to just move the list. We need to relocate the products based on their new hash values. So in order to do that, just delete this part, relocate. Okay, here we copy all the existing lists. We don't want to do that. We just want to create a new array of hash tables. Okay, so this is a solution that will always work, but is not efficient. Let's go to resize hash table. We will actually rewrite this function from scratch. So we start with a new size. We have the new array here, created here. Delete also this part. We don't need to copy any lists from anywhere. We just initialize all the pointers here to null. So we have a new array of lists. They are all null. And what do we do now? We go through all. So we go through the previous hash table and reinsert all existing products. Now that will take a lot, but let's say we don't need to do this too many times. Maybe we will start with the larger size, like 10,000, and after doubling that, it's 20,000, 40,000, 80,000, 160, and now it will grow very fast to millions and billions. So we go through the previous hash table and reset all existing products. How do we do that? For integer I starting at 0, I less than hash table number of elements, okay, I plus plus. And now we need to go through all lists. So go list by list, which actually means for, let's see, for node P, starting at hash table array of lists at index I, and this is the head. P is different than null, so we don't want to consider null, and P is equal with P next. Okay, so starting, we go through the current list. We are here, okay, and this will go through all the elements of the previous hash table. So now we have each product in the current list. What we do now is this: int index, new index, equals with hash function of P product barcode, and the size here is the new size, okay, because we want to see where this product will go in the new array list, which has been resized, okay, is the resize hash table. So we got the new index here, and now we go there and we are using the function we have written here, insert at head. So will be like this: new array at index new index equals, and this is the head. It may be null, but we covered that here. Insert at the head is insert at head, which is the current head. New array at new index, and the product, which is P product. Okay, and now all the values will be reinserted in the new hash table. Because here we are doing actually inserted the head, new array on new index, if initial is null, inserted the head will insert this new product as the new node, and that's it. So when these two loops, so this goes list by list, actually the comment is here, and here is like go product by product or node by node in the current list. Okay, so we go to the previous hash table, we go through all existing lists if they exist or until we reach null. We compute the new index of that product there based on the new size. We have the same function, but the size is different and it's the same barcode. We get the new index and now we build up from 0 the new array. And that's it. I think this will cover all corner cases. Now, it will take time to relocate all the products, but let's say we start with a 1 million size hash table, okay? And after that, we resize it to 2 million, 4 million, and maybe the number of resizes is not so big. And yeah, but this will take time. Maybe we will find out until next time. I will search for that. Maybe you find, we can discuss on Slack for new approaches here. But this is not a rush solution. It will always work, but it's not efficient. Okay, but sometimes it's the safest way. Okay, so let's say it's the simplest way in this case. Okay, so this is what we have done. We just relocated all the products and then this. So this is actually resize hash table. We created a new array of lists. We went through the existing array of lists and we relocated all the products. Okay, now the problem is here that when we free the previous hash table, this will generate memory leaks. So here to do, we need a function that will delete previous lists. Okay, so this is something we need to do. Okay, now let's go back. So this is the resize. Inserted head is in searching. Search for product is searching in a list. Insert product into catalog, and we stop here. So here we get the dictionary and the product is, if this is null, returns 0. List index hash function of product, okay. We got the list index, and now I think this is easy. It's catalog. What we need to check if when we insert a product into catalog, we need to avoid duplicates. This is another issue. Remember, when we are talking about a key, we should have the same value only once. So let's check for duplicates. How do we do that? By using the search for product function. Product existing equals with search for product, where at this index, because we know that's the location of the product, so it'll be dictionary catalog arrays of list at index list index. We check for duplicates. Existing equals search for product into dictionary catalog array of list index. Okay, and the barcode is this product barcode. Now we know that if the product exists, so it has a name, a description different than none. Remember, if we search is none. So if string compare of existing dot description against none, you need to check this one because it's case sensitive. So if this check is different than 0, it means they are different. Okay, let's see, string compare. Yeah, I don't know, this is the IntelliSense. It's always adding a a bracket here. So if string compare between existing and description and none is different than 0, it means only one thing. It means, and I think this one is, okay. It means that we already have the product. So the product is already in the table. So what we will do now is to update its data. Okay, so I will say existing. Yeah, but this is the product. Okay, so let's say we don't want to, because if I change existing, I'm not changing the value inside the list. The product is already in the table. So we will return 0. We don't insert it again. Return 0. Okay? Else means it's a new product. So it's a new product. So we need to insert it here in the in this list. So let's insert it. Dictionary catalog array of lists at index list index equals with insert at head of this head and the new product. Okay, and here return 1. Okay, so this is inserting in the hash table. What we have done, we computed the index of this new product by using the same hash function. We have checked for duplicates, which means we search for the product in the hash table, okay, at this location by using the barcode of the new product. Now, if the resulted product from search for product has a description equal to none, it means it's a new product. Okay, we are searching for a product that doesn't exist. We don't have that barcode there. So dictionary catalog array of list index, this is the current list in which this product should go, equals insert at head. Okay, and we get the insertion and we return 1. Now, if the product is already there, which means we get an existing product with the description, okay, it means it has the same barcode. We can check the barcode, for example. And I think this is more properly to check the barcode of product against existing. Okay, it means the product is already in the hash table, so we return 0. So this will be insert product into catalog.
Question: if
yes,
we are modifying dictionary, shouldn't we pass it with the address?
We don't modify the dictionary because we actually modify the pointers inside the array list. We don't change this pointer. It's the same array list. Its values.
Yeah, we're modifying with the inserted head.
Exactly. So we change only the values inside the array, but the array is still at the same address in heap.
Okay, thank you.
So we update the values. Okay. If you have a function and you give me the array address and you change values from the array and not the pointer itself, when you get out of the function, the values are changed, right?
Yes.
Okay. So now we have the insert product into catalog. Okay. Now let's do that. Let's see if we get a crash or something. So let's create a product. E1 equals product. Let's say, yeah, this is not an object. Let's see description, price, stock, and barcode. Let's say soda. The other one was what? I need a price, stock, and barcode. Price 3.3, stock 100 items, and barcode. Let's say 2A345, whatever. Okay, doesn't matter. Okay, let's create a new one. Let's say this will be, I don't know, let's say bread, different barcode 456AV, and this will be salad. Okay, with a different price here. Let's say 1,000, and here are different price. Let's go for 9.6, 50 items, and now for the salad, I will go for 1, 2, 3, 4 ZX. Okay, so we have these products P2, P3. Okay, so let's insert them. Insert product into catalog. Let's say store catalog, and the product will be P1. Duplicate this line. Let's insert P2 and P3. Okay, now we can do a wrap around the search catalog function in order to search for a barcode. And this is very simple to do. Let's build the project. Build the project. Okay, my normal issue. You don't have this one, but this is an issue that we should all have. Insert that head, and we know what's the problem. The function is defined here. Let's move it before resize. Okay, and I need to deal with the use CRT. So just remove the insert that head before resize, because we need we use that function there. So I need my macro symbol. So define CRT secure, no warnings. Okay, let's rebuild it. Rebuild. It's with the underscore here. Sorry. Build, rebuild. Okay, so I have 0 errors. And like I said, you should all have at least one error, which is the one with insert at head, and you need to move it before resize hash table. Okay, so the last function will be a check or a search. So product, search catalog.
And we didn't modify the stock for when we insert the product.
Okay, this is the issue. You see here, we choose this approach.
We can make a function, a simple function for that.
For what? To change what?
The stock.
Where here in insert is like you insert the product again and you want to update the stock with the new value, or increase the stock?
Yeah, we increase the stock.
Okay, so if we want to do that, what we really need here to change the stock here, we need an address, not a product. You see why? Search for product is actually giving us a copy of the product insert, which is inside a list, right? If you get a copy of it and you change the copy, this is a copy. What do we change? The copy or the real product inside the list? Here. So we are changing the copy, right?
Yes.
Sorry, my microphone muted.
But you got the idea, or?
Yeah.
Okay, so this is the problem. When we search for a product based on a barcode, let's suppose we find this one. It's here. This is the product. Our search function is actually returning the copy of the product. So you will get a copy. Let's say this is the copy. This is the return. Now, if we change the stock here, this will not affect the stock here. So how can we change the product here? We need to change search in order to give us what? Not a copy, but the address. Remember, anytime you need to go somewhere in memory and to write or read, you need the address. So in order to make that work, we need to actually to update search for product in order to give us this. So, okay, so I'm focusing on search for product. So we need its address, not the values. Now, this is actually helpful because right now we don't need to return a generic result because here we need a pointer. So what's the best way to say the product is not there when you are asking me for its address?
Null. With an
Exactly.
exception.
No, we can't throw exceptions. We are in C, sorry. Okay, if we were in Java, that will be another case. So return null, which is perfect. We don't need a generic product. I deleted the first line. Now for node, return what? Its address. Okay, and if we reach this point, return null. And I think it's more clear than the previous version by returning the pointer. So if the list is empty, say we can't find anything, null. We go through all the products, and if we find that particular one, we return its address. And otherwise, if we are out of the for, it means the product is not there. Return once again null. Okay, so let's go back here into search product. Now, this is not a product, is the pointer. So we get this. Now, this is even more simple. We don't need this if. It's like if existing different than null, which means we found it. The product is already in the table. So what do we want to do? We update the stock, right? That was the idea.
Yeah.
Yeah, let's say we update the stock and maybe the price. Now you can do anything with that product. So in this case, existing stock, do we want to replace it or we just say?
We just increased it with one.
Not with one.
Oh, with the stock, sorry, yeah.
Exactly. Product, stock. Okay. And actually, this is the way we should wrote search for product in the first place, because now we are more flexible. We can actually do whatever we want with this. Okay. So here we still return 0 because we want to say there was no update, no insert. Maybe we can create a code. So let's say 2 means update, we updated the stock. So let's put here at return 0 for empty list, return 1 for new inserted product, and at return, this is the way in C you can communicate different stuff by codes, return 2 for product stock update. Okay, so in this way we say no insert, we have an update or a new product. Okay, so let's wrap this in a product search catalog. What we need a product catalog, products catalog. So let's say PD. Okay, PD. Okay, and the barcode. Const char barcode. So what we will do, we will use the search for product, but in order to that, we need the list. So once again, int list index equals with the hash function of barcode, the received barcode, and the table size, which is here, PD dot catalog dot number of elements. Okay, we got the list index. Now we say product asterisk existing equals with search for product here in the head, which is PD catalog array of lists at list index, okay, and the barcode. Now we check if we found the product. So if existing is null, let's be pessimistic, we didn't find it, and I think this is where we return the product. Return create product of none, -1, -1, and empty string. Else return the value from that pointer, because we got the pointer. And in this way we also protect our products. Okay, we don't return their addresses existing. Okay, let's test this. So here we inserted something in the catalog, and okay, so this was the function existing null create product else return existing. Okay, and now we want to check this. So print product of search catalog for into store catalog, and the barcode, let's search for this one. Okay, now let's see if we are lucky. Control F5. Okay, I will show you the console. I will write another one. Control D. Let's search for salad. Okay, and also let's search for something that does not exist. A23. So Control F5. Okay, I will switch to the console window. So this is it. So bread, barcode, salad, barcode, none, price, stock, barcode. And now this is the moment of truth. Now let's do a resize. This will be interesting. And after that, let's search for them. This is the resize test. So resize hash table, products catalog. So resize hash table, products catalog. Sorry, store catalog in our case. Resize hash table, store catalog dot catalog, and we pass the address of this structure. Okay, like this, which is our hash table in the store catalog. We are not defining a function, we are just calling it. So here we have a new resize. In order to see if this works, let's check the, I want to show you that I'm not tricking you. So print f, let's say new size is, sorry, it's not Java, %d, store catalog, catalog number of elements. So here we need to see 203. And once again, let's check this stuff. Okay, so once again, Control F5. Let me share the console. Okay, so you see the new size is, here I need the \n, but it's visible here. And now we have the same stuff here. Okay, so now these are the main operations. We lost some time by redesigning resize, but I think that was actually a good thing, because now we have a deeper understanding of what's happening there. Now, in order to truly finish this example, you need only one thing to add, and is the to-do method here. Okay, so you need a function that will delete actually a list. Okay, so in order to delete a list, a simple linked list, I will give you the method, and you need to reuse that to delete the array of lists. So I will write it here. Function that deletes a simple linked list. So you have its node and you want to delete it. Void delete list. So you have the node head. Okay, remember, we need to delete it, but the problem is that each node has the address of next. So we need to be very careful, because if we delete the current node, we lose the next. So this is actually the thing that we need to worry about, not to delete the current node until we got the next node address. So one way of doing this is this. While, let's define a P node, a temporary node. So node P equals null, or temp, okay, and no, equals head. So while temp different than null, okay, and in this way we cover the case when the list is empty. It's already empty. This will not execute because the temp is already null. But let's suppose it's not. We need to save the next node, and after that to delete, because if I do temp equals temp next, now I can't free temp or the previous node. I'm already on the next one. So here I need something like node P equals temp equals temp next, free P, free Willy. Okay, so this will clean up the list. Okay, so you get the current node, which is temp, which starts at the head. Now you move this temp to the next one, and now it's safe to delete P, okay, which is the node from which you moved away here. And when you reach the end of it, let's say P will be actually the last one, temp will become temp next, which will mean null. You delete the last one, and when you go back here into the while, temp is already null, you exit. So this is how you delete a simple linked list, and you need to use this in order to delete all the other nodes here, okay? Because this will delete the array of lists, and yeah, so I think it's simple, yeah. Let's write that. Int I at index 0, I less than, okay, I less than, what's the size of it? Hash table, array of number of elements, I++, delete list of hash table, array of lists at index I. Now you have it, okay? Delete the lists. Okay, and you need to move the function. You'll have a compiler error. Now delete the array. So in this way we clean up, and we delete the previous array list which had the smaller size. And the only need that you need now is to move this function here. Okay, we need to move it before resize. That's here. Okay, so function that deletes a simple linked list, it's here, and now you have the cleanup. Okay, so yeah, that's it. That's the entire example. Now, even if we went for this direct solution, we still needed some extra time to finish this, and I think resize has required a lot of time to redesign it, thinking of it, and so on. But if you just stick to an initial hash table and that's it, and you don't resize it, you don't need the resize method. Yeah, at some point it will be less and less efficient because you have more and bigger lists, but it will still work. Now, if you choose an initial hash table with, let's say, 1 million lists, that will be okay. So until you reach that point where it will be inefficient, I think you will have other issues with RAM and other stuff. But without this, the other operations, they should be clear. Search for product, insert product. Okay, so if you just ignore resize, the other methods should be clear enough to understand this.